Hi everyone! Today I would like to present to you one of my recent works. It's called T-Star. In this work, we invent a context-aware transformer framework that is both model agnostic and enabled to offer probabilistic demand forecasting for an ultra short-term interval in the future. In this case, we perform a case study for a dock-based shared micromobility service in Washington, D.C. My research work is sponsored and related to SUM, which is an EU co-funded project focused on promoting seamless shared urban mobility. I would like to start my presentation with a joke, which may call to our common experience with shared mobility. Imagine there is a sunny day. You are about to get out of a metro station and you are thinking, the weather is so amazing. So instead of taking the bus to the park for picnic, I will ride the bike. However, at the same time, everybody were coming after the bike and you were like, oh my God, but there is only one bike available. From a passenger perspective, this can be really annoying. But from the company perspective, this is also one of the main challenges. How do we know whether there's a certain surplus of demand for bike sharing? This is what we are going to study. But before going into the matter itself, I would like to mention a couple challenges for demand and fleet availability forecasting in practice. So first of all, a company needs to be able to integrate multiple sources of information to address the uncertainty as the nature of shared urban mobility itself. There are also a couple barriers of security for this information to be gathered and merged together. The second aspect is about providing a detailed and up-to-date prediction by the tool. In urban mobility, there are some hours that you might observe few or even no demand, while there are other times of the day that the demand is so high that the system goes under supply. And by analyzing all these existing challenges as well as the current study in the literature, we summarize the research gap. First of all, there is a lack of attention to generate a robust predictor that can handle prediction in a high granularity setting. And the granularity in spatial and temporal level are crucial, especially for dock-based shared mobility. Secondly, we would like to address all sorts of uncertainty existing in the environment, especially in the ultra short-term time periods, like the next 15 minutes. Uncertainty of demand may arise from the delay of the connecting metro, or even a promotion event by the service itself. Therefore, we would like to have a model that can capture both the external factors, such as multimodal transit operation in the mobility hub, as well as internal causes for this demand variation, such as undersupply of the fleet. Lastly, which is also important for this urban platform, is to create a model that can be trained adaptively and be able to generalize its performance across both old region and also new service region they intend to establish in the city. It should also be scalable in the sense that perhaps more than 200 stations in the city would require the prediction in real time. That calls for the research objective of this study. So we aim to develop a short-term demand forecasting framework that can deliver robust and accurate prediction in a high temporal resolution. Secondly, we would like to strategically integrate multiple sources of uncertainty from both the environment, from the public transit infrastructure, as well as the weather information, which influence the passenger behavior. Lastly, this model set out to capture the short-term demand fluctuation, which can be caused by multiple factors, including the supply issue of the platform, as well as other issues that are not being able to be captured through the feature input set. In this study, we performed the analysis through a dock-based capital buy share in Washington, D.C. The data is open source and allows for fair comparison with all existing models. The main novelty of T-star stands in how to utilize the demand variation signals. As we mentioned before, this type of uncertainty existing in the environment are not always being able to be captured or described through the feature set. In T-star, we really look into the deviation signals to see what would be the trend of the next observation. For instance, if we observe a consistent upwarding trend for demand, we also tend to predict perhaps the future demand will also be higher than what's expected. However, at the case when the station goes under supply, which means there are no available vehicles to be used, then in this case, the consistently lower than expected demand also says something about this station needs to be maintained before it can go back to the normal demand pattern. Utilizing this observation, we propose the transformer-based T-star framework. It may be really complex with a lot of steps from this diagram, but let's break it down into 4 modules. The first module is the time series inputs, alongside with the various sources of contextual features, such as weather information, the recent operation details about the connected public transit, as well as the station criteria, which are static features to describe the capacity of this bike-sharing station. And the second module contains the estimation of expected demand pattern. By aggregating the demand through a longer time interval, we get the time series at hourly basis, which is less zero inflated and tell us more about the regular pattern of demand. And the third, we extract the demand variation by comparing the per 15 minutes demand against the expected demand level we estimate from the second stage. And these variational signals are used jointly as inputs alongside the contextual feature into the last stage, where we perform per 15 minutes demand prediction and output the most possible distribution of next interval's demand. And to work with the T-star framework, we select the time series transformer. Transformer is a powerful deep learning tool originates from the large language modeling studies, but recently it has been extended to perform time series forecasting as well. It is, first of all, a global predictor that is available to generate prediction for a large set of stations. In our case, we have 235 bike-sharing stations in the dataset, and is capable to generate for all of them for the next time interval. Second of all, it also supports few short learning that makes the the model more adapted to future data that the company would gather, which also adapts to the ever-changing urban mobility environment exists in the city. And it's also very adaptable. Companies can use this model pre-trained and without any additional information to just test it on the new service station, which typically has zero demand or historical trip information. It's also able to provide the probabilistic demand prediction based on the assumption. In this case, when you want to predict for a couple time interval in the future, you can use a decoder to enable teacher forcing. However, if you are only interested in predicting one step ahead, decoder would not be necessary. In the experiment, we try to analyze the additional benefits provided by including multiple sources of uncertainty. So we create 4 different input type scenarios. By trying out different level and different detail level of the input types, we also analyze this combination with the state-of-art based predictors. We would like to highlight, for our transformer-based T-star model and with all the input features are included, we perform the best among all SOTA model analyzed here on the Washington, D.C. dataset. In a short summary, compared to a simple time series input only transformer model, the T-star transformer achieved in close to 20% of improvement for MAE and also more than 40% of improvement on MIS. If we want to visualize and look one step closer to the performance for different types of station, we notice there is a huge improvement, especially for the high demand area. The other question we would like to explore is how generalizable is our T-star framework. Again, T-star framework itself is model agnostic. The only addition it's trying to pull is by analyzing the demand variation as additional inputs in the second stage. And by separating the training of expected demand pattern and the short-term demand expectation, T-star use this magic to improve the future prediction by integrating what is expected and what is the deviation. So we apply T-star for 4 different base predictors. The result shows that the performance, regardless of the type of base predictor, always improves by using T-star. The last question we would like to explore is what would be the zero-shot capability of T-star transformer. And in this case, we select 11 bike-sharing stations which are connected with a nearby metro service in the Arlington area. And by using different predictive models that we already pre-trained and a fundamental time series model like Llama for the comparison, we highlight that the zero-shot transformer-based T-star consistently receives the highest point prediction accuracy, highlighting the deep learning-based model is able to predict without extra effort, which is a nice property for company to have. To summarize, in this study, we addressed the challenge of creating a reliable short-term predictor for shared micromobility system, where we would like to have prediction that is accurate at the high spatial and temporal resolution setting. With this aim in mind, we propose T-star, a two-stage model agnostic model that is able to integrate multiple types of contextual inputs and jointly capture the long-term expected demand pattern as well as addressing the short-term demand variation in one place. For the case study using capital buy-share data from Washington, D.C., we have examined and compare with different types of model combination with SOTA baseline model as well as different level of details contained by the input setting. The result highlights that T-star model combined with time series transformer consistently outperform when we look into different perspectives of accuracy and robustness of this prediction, showing that it's capable to predict accurate yet reliable, scalable, and generalizable prediction for a large-scale urban shared micromobility network. Thank you very much. If you're interested in learning more about the paper, you can look up the repository online, where we have both the manuscript and the open source coding. Thank you.